A telescope aimed at a galaxy so far away that its light left before Earth existed picked up something that our best physics says should not be there. James Webb is doing this repeatedly. Massive galaxies forming too fast, atmospheres carrying molecules that life makes on Earth, disks, rings, and structure appearing in places where chaos was expected. Each image arrives and quietly pulls one more thread from the fabric of what we thought we understood. We are going to walk through the most confronting things Webb has caught. A star forming right now in real time. A planet with chemistry that stopped researchers mid-sentence. Galaxies so old and so large they compress billions of years of cosmic history into a space that should have held almost nothing. And one object at the absolute edge of Webb's range that, if confirmed, breaks every timeline we have. If you want to keep following discoveries like these, subscribing helps us keep going. Stay with us. Every chapter ahead gets harder to explain away. For decades, the universe had a hard edge, a boundary we could not see past, set by the limits of our instruments. Then, in July of 2022, that edge dissolved. James Webb Space Telescope sent back its first full-color images, and astronomers around the world went quiet. The data arriving on their screens showed objects so distant, so ancient, and so detailed that several researchers described the experience as genuinely disorienting. These were real scientists who had spent careers preparing for this moment, and the results were still landing outside what they had prepared for. To understand why, you need to picture what Webb actually does differently. Every telescope before it looked primarily at visible light, the same narrow band of color the human eye detects. Webb operates almost entirely in infrared, which is heat radiation. When light from the early universe travels across billions of light years, it stretches, its wavelengths grow longer. By the time ancient starlight reaches us, it has shifted entirely out of the visible range and into infrared. Visible light telescopes were essentially blind to the earliest chapters of cosmic history. Webb was built to read exactly those chapters. Its primary mirror spans almost 21 feet across, that is, roughly 2.5 times the width of the Hubble Space Telescope's mirror. More collecting area means more light gathered, and more light means sharper, deeper images of fainter, older, more distant objects. Webb also operates from a position about 1 million miles from Earth, orbiting a gravitational balance point called the second Lagrange point, where it stays cold and stable, shielded from the heat of the Earth and the warmth of our star. The cold matters enormously. Infrared detectors must themselves be kept near absolute zero to function. Any warmth in the instrument would flood the sensors with their own heat signal, drowning out the faint glow of ancient galaxies. Webb carries a sunshield the size of a tennis court, made of 5 layers of reflective film, each thinner than a human hair, to maintain that deep cold on its instruments while one side bakes in sunlight. All of this engineering existed in plans and proposals for over 2 decades before launch. The telescope was first proposed in the 1990s, survived multiple near cancellations, cost roughly $10 billion to complete, and launched on Christmas Day of 2021. It deployed its mirror and shield over the following weeks, a sequence of 344 individual mechanisms that all had to work perfectly the first time, with no crew available to fix anything. That launch worked. Every mechanism deployed correctly. 6 months later, the science began arriving. And almost immediately, the findings started pulling at assumptions that had held for a generation. Astronomers had built detailed models of how the early universe should look, how structure should form, how fast galaxies should grow, how organized or chaotic the first cosmic objects should appear. Webb's first year of data did not simply confirm those models with higher resolution. In several key areas, it contradicted them, quietly, precisely. With data solid enough that the contradictions could not be dismissed as noise, the first anomaly Webb exposed was also the most fundamental. It concerned the very oldest galaxies Webb could detect, the ones that formed when the universe was barely getting started. The models said these should be small, dim, and irregular. Webb found something else entirely, and the gap between prediction and reality turned out to be enormous. The universe has an age, roughly 13.8 billion years, measured through multiple independent methods, with high confidence. For most of cosmic history, that number felt like solid ground. Then Webb began photographing the early universe, and the timeline started feeling much tighter than anyone had expected. In the first year of Webb's science operations, teams analyzing its deep field images identified a population of galaxies that existed when the universe was between 300 and 700 million years old. That sounds like a long time, but on cosmic scales, it is barely a breath after the beginning. For context, our own galaxy took billions of years to build itself into the structure it holds today. The expectation was that galaxies at this extreme age would be small, diffuse, and still assembling. Several of the galaxies Webb found were already massive. One candidate object, studied by multiple teams and published in early Webb science papers, carried a mass comparable to our own galaxy, but existed when the universe was only 3% of its current age. Researchers describe this as deeply puzzling. Under standard cosmological models, the universe at that point simply had not had enough time to build that much stellar mass in one place. The problem is rooted in how stars form. Gas has to collapse under gravity. That collapse takes time. The gas has to cool, fragment, and condense into stellar nurseries. Then individual stars ignite, burn through their fuel, explode, enrich the surrounding gas with heavier elements, and allow the next generation of stars to form. This cycle, stacked over and over, is how galaxies grow. Running it fast enough to produce a massive, well-formed galaxy in under 1 billion years requires conditions that our best models struggle to accommodate. A team led by astronomer Ivo Labe published findings in early 2023, showing that the abundance and mass of these early galaxies exceeded model predictions by factors that could not be explained through minor adjustments. The shortfall was large. Some models would need to be revised at a structural level to account for what Webb observed. There are competing explanations currently under active debate. One possibility is that star formation in the very early universe was dramatically more efficient than it is today, converting gas into stars at rates we have never witnessed in the modern universe. Another possibility involves the role of supermassive black holes in the centers of these young galaxies, which may have driven an extraordinary burst of star formation before eventually shutting it down. A third possibility, more unsettling, is that some of our assumptions about how dark matter clusters in the early universe need revision. None of these explanations is confirmed. Scientists are careful to say that the mass estimates themselves carry uncertainties, and some of the most extreme candidate galaxies are still awaiting deeper follow-up observations to nail down their true distances and stellar content. What is clear is that the earliest universe Webb can see looks more structured and more massive than models built on decades of observations predicted. The pattern across multiple independent datasets points consistently in the same direction, and this early galaxy problem is tightly connected to a second tension that Webb did not create, but has significantly sharpened: a disagreement about the expansion rate of the universe that has divided cosmologists for years, and that Webb's precision has made considerably harder to ignore. Two measuring tapes, same universe, two different answers. Cosmologists have two independent ways of measuring how fast the universe is expanding. The first uses the afterglow of the Big Bang, a faint signal of ancient radiation, called the cosmic microwave background. By studying the detailed pattern of that radiation, physicists can calculate what the expansion rate should be today. The second method measures it directly, using nearby objects like pulsing stars and exploding stellar remnants as distance markers. You measure how fast those objects are moving away from us. You compare it to how far away they are, and you get the expansion rate. The two answers disagree. Significantly, the discrepancy is called the Hubble tension, named after the expansion constant these methods are trying to measure. The disagreement has been known for several years, but for a long time astronomers hoped it would disappear once measurements became more precise. Webb was supposed to help resolve it by sharpening the nearby measurements, removing sources of error in the distance ladder method. Webb sharpened the measurements. The tension did not go away. A major study published in 2004 using Webb data on Cepheid variable stars, the pulsing stars used as cosmic distance markers, found that the discrepancy held up even after correcting for sources of contamination that older telescopes could not resolve. Crowded star fields that Hubble could not separate cleanly were now separated cleanly by Webb, and the numbers still disagreed with what the cosmic microwave background predicted. The gap sits at roughly 8 or 9% between the two methods. In everyday terms, that sounds small. In cosmology, where precision is the entire foundation, it is a significant crack. Either one of the measurements carries an error that has not been found yet, or there is something about the universe's history or composition that our current model of cosmology does not include. The standard model of cosmology is called lambda CDM. Lambda refers to dark energy, the force believed to be accelerating the universe's expansion. CDM stands for cold dark matter, the invisible scaffolding believed to shape how galaxies form and cluster. This model has been extraordinarily successful at matching observations across many scales. The Hubble tension is one of the places where it currently has no clean answer. Some researchers propose that dark energy is evolving over time rather than staying constant, which would affect expansion history in ways that might close the gap. Others suggest an early burst of additional energy in the universe's first moments, sometimes called early dark energy, shifted the baseline. Measurements released in 2024 from a large galaxy survey called the Dark Energy Spectroscopic Instrument added further pressure to the constant dark energy assumption. What Webb contributed here is clarity. It eliminated a measurement source of doubt, not the doubt itself. That matters because it means the tension is real. The universe's expansion, measured two different ways, gives two different answers, and the best telescope ever built has confirmed that the gap is not an artifact. Something in our picture of the cosmos is incomplete. The question spreading through cosmology now is whether the fix requires a small correction or a structural rethink. Until Webb, the idea of reading the chemical composition of a planet's atmosphere from over 1,000 light-years away was theoretically possible and practically out of reach. The signal was too faint, the interference too heavy, the technology not yet sharp enough. Then Webb turned toward a gas giant called WASP 39b, and the field of exoplanet science moved forward a decade in a single observation. WASP 39b is a gas giant roughly the mass of Saturn, orbiting its star so closely that a full year on that planet lasts only about 4 Earth days. Because it orbits so close, it periodically passes in front of its star from our perspective. When it does, starlight filters through the planet's outer atmosphere before reaching us. Different molecules in that atmosphere absorb different specific wavelengths of that light. Webb, with its infrared sensitivity and its enormous mirror, can detect those absorptions with enough precision to identify individual molecules. In a set of papers published in late 2002, a large international team reported the most complete atmospheric profile ever assembled for a planet outside our solar system. They found water vapor, sulfur dioxide, carbon monoxide, sodium, potassium, and critically, carbon dioxide, confirmed with a strength of signal that left no room for doubt. That carbon dioxide detection was a landmark. It was the first unambiguous chemical signature of this molecule ever caught in an exoplanet atmosphere, and it demonstrated that Webb could do this kind of chemistry at a level of detail that would have seemed optimistic just 5 years earlier. The sulfur dioxide detection carried its own surprise. The molecule was forming through a process called photochemistry, meaning the planet's upper atmosphere was being chemically altered by radiation from its star in real time. The models had predicted this should be happening, but seeing it confirmed through direct measurement gave researchers a tool they had not had before. Why does this matter beyond scientific curiosity? Because the same technique, the same method of reading atmospheric chemistry from starlight, applies to smaller, cooler, more Earth-like planets. WASP 39b was the training run. Scientists now know the instrument works. They know how to interpret the data, and they know which molecules leave which fingerprints. The next step was to aim that technique at planets where the conditions for life as we understand it might exist. That next step happened faster than most researchers expected, and the molecule it found was one that nobody in the scientific community felt fully prepared to discuss without careful language and heavy qualification. On Earth, there is exactly one known process that produces this molecule in meaningful quantities. That process is biological. Researchers were careful, measured, and deliberate in how they described what Webb detected, but the detection itself could not be ignored. The planet where Webb caught this signal is cooler than WASP 39b, sits in a range of distances from its star where liquid water might exist, and carries a type of atmosphere that some models describe as potentially ocean-covered. The name of what Webb may have found in that atmosphere, and what it would mean if confirmed, comes next. K2-18b is a planet roughly 8 to 9 times the mass of Earth. It orbits a red dwarf star, about 120 light-years from us. It sits in the habitable zone, the range of distances where liquid water can exist on a surface, depending on the planet's atmosphere and composition. Scientists have been interested in this world for years, but lacked the tools to see inside its atmosphere clearly. Webb provided those tools. In September of 2003, a team led by researchers at Cambridge University published findings from Webb's infrared observations of K2-18b. They confirmed carbon dioxide and methane in the atmosphere, both consistent with a world that some theoretical models describe as a Haitian planet, meaning a world with a hydrogen-rich atmosphere and a global liquid water ocean beneath it. The Haitian class is theoretical. It is a model, and the jury on whether K2-18b actually fits it is still out. Then came the part that required careful handling. The same dataset showed a potential signal for dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, microscopic ocean life. It is the molecule responsible for the distinctive smell of the sea. As far as we know, no geological or purely chemical process generates it in significant quantities without biology involved. The team was deliberate and precise in how they framed this. The signal was tentative. The confidence level placed it in the category of something that needs confirmation from additional observations, not something that can be claimed as detected with certainty. Several other researchers responded publicly, noting that the signal could also reflect an instrument artifact or an atmospheric chemistry pathway involving non-biological sulfur compounds that we have not fully characterized for a hydrogen-rich atmosphere under those specific conditions. This is exactly where honest science operates: a possible signal, competing explanations, a need for more data. What the finding did confirm is that Webb is now sensitive enough to detect this kind of molecule at that distance, in those concentrations, under those conditions. That sensitivity itself is the milestone. Whether this particular signal holds up under further scrutiny, the capability it demonstrated now exists and will be applied to other targets. K2-18b will be observed again. The teams that analyzed the original data are already working toward follow-up observations that could either strengthen the dimethyl sulfide signal or explain it through non-biological chemistry. That result has not arrived yet. Meanwhile, Webb was gathering a different kind of atmospheric data from a planet with far bleaker implications. A world that many researchers had hoped might show signs of a complex atmosphere turned out to carry almost nothing above its surface, suggesting that the most common type of star in our galaxy may be a far more hostile host than anyone wanted to believe. TRAPPIST-1 is a small, dim, cool, red dwarf star sitting about 40 light-years from Earth. Around it orbit 7 rocky planets, several of them sitting at distances where temperatures could, in theory, allow liquid water. For years, this system carried enormous symbolic weight in the search for life beyond our planet. 7 rocky worlds, 3 in the habitable zone, close enough for detailed study. Webb was always going to be the instrument that finally told us whether any of those worlds had held onto an atmosphere. The results came in stages, and they were sobering. TRAPPIST-1b is the innermost planet, closest to the star, and certainly too hot for life. Webb measured its thermal emission, the heat radiating off its day side, during a secondary eclipse when the planet passed behind the star. The temperature came back at roughly 447 degrees Fahrenheit on the side facing the star. That is close to what you would expect from a bare rock with no atmosphere at all. A substantial atmosphere would redistribute heat around the planet, lowering the dayside temperature. The reading Webb got matched a world stripped clean. TRAP PIST 1c sits slightly farther out and was the more important test. It receives roughly the same amount of stellar energy as Venus does from our own star. If TRAP PIST 1c had a thick carbon dioxide atmosphere like Venus, Webb should have detected a specific level of thermal emission. Instead, the measurement came back much lower, closer, again, to what a bare, airless rock produces. Published in 2023, this result led researchers to conclude that TRAP PIST 1c very likely has at most a thin, tenuous atmosphere, if anything at all. A thick atmosphere, the kind that might support surface liquid water, or any kind of chemistry we associate with habitability, appears absent. The implications reach beyond these two planets. Red dwarf stars like TRAP PIST 1 are the most common type of star in the galaxy. They are long-lived and numerous. For decades, the idea that their habitable zones could host life made red dwarfs attractive targets in the search for biosignatures. But red dwarfs are also magnetically volatile, especially when young. They emit intense ultraviolet and X-ray radiation in frequent flares. Webb's findings on the TRAPPIST planets suggest that for rocky worlds orbiting closely enough to be in the habitable zone of a red dwarf, those flares may strip atmospheres away faster than they can rebuild. That finding does not close the door on life around red dwarfs entirely. Some models suggest planets in these systems could replenish their atmospheres through volcanic outgassing, or that certain orbital geometries offer more protection. Those are possibilities, not confirmed solutions. What Webb has provided is a clear, measurement-based signal that habitable zone rocky planets around red dwarfs face a severe atmospheric retention problem. The search for life continues, but the list of promising environments is being refined in real time, and some of the most popular candidates are proving harder to defend than the optimistic models once suggested. The next world Webb examined held a completely different kind of surprise. A planet that kept its atmosphere, carried a rich chemistry, and had resisted every previous telescope's attempts to see inside it, until Webb finally cracked it open. GJ 2014b is a super-Earth, a planet larger than Earth but smaller than Neptune, orbiting a dim red dwarf star about 40 light-years away. It was first discovered in 2009 and almost immediately became one of the most studied exoplanets in the catalogue. The reason was its size. It sat in an interesting class between two types of worlds we have in our own solar system: rocky planets and gas giants. Theorists argued about what its interior might look like, whether it was a water world, a mini gas giant, or something entirely new. Every telescope turned toward it hit the same wall: a thick, featureless haze layer in the upper atmosphere, scattered incoming starlight in every direction, revealing almost nothing about the chemistry below. Researchers tried with Hubble. They tried with Spitzer. For over a decade, GJ 1214b simply refused to show its atmosphere in any detail. The haze was too dense, too uniform. Webb saw through it. Using its mid-infrared instruments, a team published results in 10 to 24b carries an atmosphere rich in water molecules, possibly alongside carbon dioxide and methane. The haze is still there, but Webb's sensitivity allowed researchers to probe the infrared fingerprints beneath it, with enough precision to distinguish molecules that Hubble could not separate. The water-rich signature was striking. It strongly suggests that GJ 1214b formed in a region of its planetary system where water ice was abundant, then migrated inward toward its star over time. The interior of this planet may be largely water, compressed under enormous pressure into exotic high-pressure phases that do not exist anywhere in our solar system's well-mapped worlds. Some models suggest the boundary between a watery outer layer and a rocky core, if one exists, could be made up of what physicists call superionic water, where oxygen atoms form a solid lattice while hydrogen ions flow freely through it. That is a state of matter that exists on Earth only inside high-energy physics laboratories for fractions of a second. The confirmation that Webb can cut through haze layers that defeated every previous telescope matters enormously for the broader catalogue of exoplanets. Many of the most interesting worlds in our search for atmospheric chemistry sit behind exactly this kind of obscuring haze. GJ 1214b demonstrated that the barrier is now penetrable, and the technique refined here will be applied across dozens of similar targets in coming years. What this planet also reinforced is a pattern Webb keeps producing. The worlds that were supposed to be understood, the ones that had been studied for years through other instruments, keep revealing new layers when Webb looks at them. The catalogue of what we thought we knew is being reopened, one target at a time. The next time Webb turned that infrared eye on our own solar system, it found something that even the researchers who scheduled the observation did not fully anticipate. In the cold outer reaches, around a moon that had barely been studied since a spacecraft flew past it decades ago, Webb detected a chemical that carries real weight for how carbon moves through the solar system. Ariel is one of the larger moons of Uranus. It sits in the outer solar system, over 1.5 billion miles from us, orbiting a planet that most spacecraft have barely visited. The only close-up look humanity ever got of Ariel came from Voyager 2 in January of 1986, a brief flyby that produced surface images but almost no spectroscopic data. After that pass, Ariel faded from scientific attention for decades. Webb changed that in 23, pointing its infrared instruments at Ariel during observations of the Uranian system. A team detected a clear spectroscopic signature of carbon dioxide ice on the moon's surface. The detection was clean and well above noise levels, but the location of that carbon dioxide was the part that raised immediate questions. Ariel's surface is geologically diverse. It shows evidence of past tectonic activity, with rifts and canyons carved into its crust. The carbon dioxide Webb detected appears concentrated on the moon's trailing hemisphere, the side that faces backward as Ariel moves through its orbit. That asymmetry matters. It suggests the carbon dioxide did not arrive randomly from space. Something directional is driving it. The leading hypothesis is that charged particles from Uranus's magnetosphere are bombarding the trailing hemisphere, triggering chemical reactions that convert existing surface materials into carbon dioxide. The raw ingredient is likely carbon-containing organic compounds, already present in the surface ice, being chemically processed by radiation into carbon dioxide over time. That mechanism, if confirmed, tells us something meaningful about how carbon chemistry operates across the outer solar system. Carbon dioxide is a building block in planetary science. Its presence on Ariel's surface points to active chemical processing happening on a moon that we had barely classified as scientifically complex before this observation. The outer solar system is full of icy moons. Many of them orbit in magnetospheric environments, similar to Ariel's. If this radiation-driven carbon chemistry is common, the inventory of chemically active surface environments in our solar system expands considerably. There is also a deeper question sitting beneath this finding. Some of those outer solar system moons carry subsurface liquid water oceans. Europa around Jupiter, Enceladus around Saturn. Whether Ariel has a similar interior is unknown, and Webb's surface observation cannot answer that directly. But carbon chemistry on the surface is one piece of the larger picture of what these moons carry and what processes are running inside them. What Webb did with Ariel in a single observation pass exceeded what was learned from Voyager 2's entire flyby in terms of surface chemistry. And this was a secondary target in a broader survey of the Uranian system, not the primary focus. Out in the cold, well beyond Ariel, Webb was finding structure in places where it was expected to find only scattered dust, a debris disk around a nearby star that turned out to be far more organized, far more layered, and far more telling about unseen planets than anyone had guessed before Webb's infrared eye resolved it fully. Fomalhaut is a young star about 25 light-years from Earth, one of the brightest stars visible in the night sky. Astronomers had known for decades that it was surrounded by a ring of dust and debris, the kind of structure that forms from collisions between rocky bodies during the early, chaotic phase of a planetary system. Hubble had imaged the outer ring. Ground-based telescopes had mapped its general shape. Webb resolved the system in infrared in 2003, with enough clarity to reveal that Fomalhaut is surrounded not by one ring of debris, but by 3 distinct nested rings, each at a different distance from the star, separated by clear gaps. Those gaps are the critical detail. In planetary science, a gap in a debris disk is a gravitational fingerprint. It means something is orbiting inside that gap and sweeping the space clean through its gravity, pulling nearby particles into its path or scattering them outward. In our own solar system, the gaps in Saturn's rings are carved by small moons. The gaps in Fomalhaut's debris rings imply planets are present, orbiting in those spaces and shaping the structure around them. Webb's image also revealed a large, diffuse structure the team called the Great Dust Cloud, a feature with no obvious counterpart in previous images of the system. One leading explanation is that it represents the debris from a recent collision between two large objects, possibly small planet-sized bodies, that shattered and spread their material in a bright cloud that is still expanding. If that interpretation holds, Webb may be imaging the direct aftermath of a planetary collision, a violent event in another solar system caught in the relatively fresh stages of its dispersal. No planets in the Fomalhaut system have been directly imaged yet. The dust and light make direct detection difficult, even for Webb. One candidate detection from Hubble, years ago, was later determined to be a dust cloud rather than a solid body. Webb's image does not confirm any specific planet, but the architecture it revealed. 3 rings, specific gaps, a possible collision cloud, all point consistently toward a system where multiple large bodies are actively organizing the debris around them. Fomalhaut sits at an age of about 400 million years, comparable in stellar terms to what our own solar system looked like when it was going through its final phase of planetary arrangement. Studying Fomalhaut gives researchers a real-time window into the kind of architecture that our own planetary system may have passed through long before Earth's surface solidified. The fact that Webb resolved 3 separate rings in a single targeted observation, when previous instruments had mapped only one, speaks directly to the step change in resolving power that this telescope represents. And it raises an immediate question. If Webb can find hidden structure in a system we thought we understood, what else is waiting in systems we had written off as simple? The answer came partly from a star not far away, around which Webb detected something that had been predicted to exist for years, but had never been directly confirmed. A type of object sitting in the blurry boundary between the largest planets and the smallest stars, finally seen clearly enough to reveal its own atmosphere in unprecedented detail. Brown dwarfs occupy a strange position in the cosmic catalogue. They are too massive to be planets, but too small to sustain the nuclear fusion reactions that power true stars. They form like stars, collapsing from clouds of gas and dust, but they never reach the critical mass needed to ignite hydrogen burning in their cores. What they do burn briefly, in their early lives, is deuterium, a heavier form of hydrogen. Once that runs out, they simply cool and dim over billions of years. Because they cool, their atmospheric chemistry changes dramatically over time. Young brown dwarfs are hot enough to carry water vapor and silicate clouds. Older, cooler ones develop methane-dominated atmospheres. At the coolest end of the spectrum, a specific class called Y dwarfs was theorized to carry ammonia ice clouds in their upper atmospheres, making them in some ways more similar to the atmosphere of a gas giant planet than to anything we typically call a star. Webb confirmed ammonia ice clouds on a brown dwarf for the first time in 2023. The target was a cool brown dwarf designated by its catalog number, part of a survey looking specifically at the coldest and dimmest substellar objects Webb could detect. The spectroscopic signature of ammonia ice was clear, placing this object in the predicted Y dwarf class with a level of chemical certainty that previous telescopes could not achieve. This confirmation matters for several reasons. Brown dwarfs are far more numerous than most people realize. Current estimates suggest they may be nearly as common as true stars in our galaxy. The Milky Way could contain hundreds of billions of them. For decades, the coolest categories were barely detectable, their existence inferred from theory and a handful of ambiguous detections. Webb is now able to spectroscopically fingerprint them properly for the first time. The ammonia detection also gave researchers a calibration point. Brown dwarf atmospheric models had predicted when and at what temperature ammonia ice should condense out of the atmosphere and form clouds. The observation matched those predictions well, which means the models of cool substellar atmospheres are largely tracking reality. That kind of confirmation has practical value. It means the same atmospheric models applied to giant exoplanets, are better grounded than they were before. There is something almost eerie about these objects. They float in space, cooling silently, never hot enough to produce visible light in meaningful quantities, detectable only in infrared. Some of them have been wandering through the galaxy for billions of years without ever having been documented. Webb is, in a real sense, finding entire populations of objects that were always there but that we had never properly catalogued. And the farther Webb looked from these relatively nearby brown dwarfs, the more the universe revealed something that felt almost deliberate in its organization. Deep in the early universe, at distances so extreme that the light arriving now left before our solar system existed, Webb began finding galaxies shaped in a way that no model of early cosmic structure had predicted. Orderly, defined, already spinning in coherent disks, at an age when they had almost no right to be. Galaxies come in shapes. Ellipticals look like smooth, featureless blobs of stars. Spirals carry rotating arms, organized into disk structures where gas pools and new stars form. Irregulars look like what the name suggests: chaotic, collision-shaped, pulled apart by gravitational encounters. Standard cosmological models predicted that the very early universe should be dominated by irregulars. The first galaxies were supposed to form in a churning, turbulent environment where frequent mergers and collisions would shred any emerging structure before it could stabilize. Disk galaxies, like our own Milky Way, were expected to take billions of years to settle into their organized, rotating forms. Before that settling happened, the early universe should look messy. Webb is finding disk galaxies at redshifts so high they correspond to when the universe was roughly 600 million to 1 billion years old. Multiple independent teams have now confirmed this pattern across different fields of view. A study published in 2002-3 analyzed a large sample of galaxies from Webb's deep field images and found that disk-like structures were far more common in the early universe than models predicted, appearing at epochs when the universe was simply too young for that level of order under standard formation theory. The mechanism behind disk formation involves angular momentum, the rotation that comes from gas collapsing into a galaxy while conserving its spin. For a disk to persist, the galaxy needs to avoid major disruptive mergers for long enough that the rotation can dominate the system's structure. In a universe that was dense with matter and rapidly building structure, the collision rate between early galaxies was expected to be high, breaking up disks faster than they could form. Yet Webb keeps finding them. Thin, clearly rotating disks. Galaxies with defined structures at distances we expected to see only chaotic assemblages. One possible explanation being actively explored is that gas in the very early universe was colder and more settled than models assumed. Colder gas can collapse into rotating disks more efficiently, without the turbulent heating that disrupts structure. Another possibility involves the strength of feedback from early black holes and supernovae. If those energetic processes were less disruptive in certain environments, disks could stabilize faster. These are live theoretical debates, and Webb data is the fuel driving them. What the observation does conclusively is put pressure on the timeline. Our best models of how the universe transitioned from featureless gas to structured galaxies are running into repeated resistance from Webb. The resistance is consistent. It is appearing in multiple independent datasets, covering multiple aspects of early galaxy structure and mass. The models are being tested across several fronts at once. And then there are the galaxies that took the timeline problem to its logical extreme. The ones that did not simply form quickly and organize, but formed quickly, organized, and then stopped. Star formation in them switched off earlier than any theory predicted was even possible. Webb caught them sitting in silence, massive and complete, at an age when they should have still been building. A quenched galaxy is one where star formation has essentially stopped. The gas that would have collapsed into new stars has been depleted, expelled, or heated to the point where it can no longer condense. In the modern universe, quenched galaxies are common. Large elliptical galaxies in particular tend to be old, red, and quiet, their stars aging and dimming over billions of years with no new generation being born to replace them. The process of quenching takes time. Star formation has to peak, run through enormous reserves of gas, and then be shut down by some mechanism strong enough to prevent the galaxy from drawing in fresh fuel from surrounding space. The most commonly accepted driver is the supermassive black hole at a galaxy's center. When it becomes active enough, it launches jets and radiation powerful enough to heat and eject gas from the entire galaxy, cutting off the star formation supply. This process, called AGN feedback, is well supported by observations in the modern universe. The models predict it should take several billion years for a galaxy to build up, reach peak star formation, and then be quenched. Webb found quenched galaxies at distances corresponding to when the universe was just over 1 billion years old. Massive galaxies, containing hundreds of billions of stellar masses worth of stars, already red, already quiet, already finished with the major chapter of their formation. Published studies from Webb's first 2 years have confirmed multiple examples, with the most extreme cases pushing into the first billion years of cosmic time. The problem is the math. These galaxies had to form most of their stars, build up their black holes to the point where AGN feedback could operate at scale, and complete the quenching process all within a time window that the models say is far too short for that sequence to run. Forming stars rapidly is one thing. Forming a massive active black hole and triggering a galaxy-wide shutdown inside the same compressed timeline is another challenge entirely. Some researchers suggest that in the dense early universe, black holes grew faster than models currently predict, driven by an abundance of available gas and different merger conditions. Others propose that supernovae feedback, the collective blast of dying massive stars, played a larger role in early quenching than previously assumed. A third possibility is that some early galaxies formed in unusually dense dark matter halos that both accelerated star formation and concentrated the conditions for faster quenching. None of these explanations is confirmed. All of them require revisions to how we model galaxy formation. The core observational result is clear. Galaxies were finishing their lives far earlier than they should have been able to begin them under any standard model. Every time Webb reveals a quenched galaxy at extreme redshift, it adds another data point to a pattern that has become impossible to dismiss as coincidence. The early universe, in Webb's view, was organized, massive, and evolutionarily advanced, well ahead of schedule. The picture keeps tightening, and the next chapter takes that tightening to a place where the stakes become genuinely difficult to process. The process of star formation had been studied for decades before Webb launched. Researchers understood the general outline. Cold clouds of gas and dust collapse under gravity, heat up at their centers, and eventually ignite nuclear fusion when the core reaches a critical temperature and pressure. The whole sequence produces young stars surrounded by disks of leftover material, which over millions of years can clump into planets. Understanding the theory and watching the early stages of it in detail are two different things. The early stages of star formation happen inside dense, opaque clouds of gas and dust that absorb visible light completely. Visible light telescopes see only the surface of these clouds. Infrared light passes through. Webb sees inside. In 22 and 22.3, Webb released images of stellar nurseries with a level of interior detail that had never been achieved. The most striking early target was a star-forming region called the Carina Nebula. In previous visible light images from Hubble, the edge of this region showed towering columns of gas and dust with nothing behind them. Webb's infrared vision cut through those columns and revealed the young stars embedded inside them. Dozens of previously hidden protostars visible for the first time, many of them surrounded by the disks from which planets might eventually form. More dramatic were Webb's images of a class of objects called Herbig-Haro objects. These form when a very young star, still in the early stages of building itself, shoots twin jets of ionized gas outward along its rotational poles at hundreds of miles per second. Those jets slam into the surrounding gas cloud and create glowing shock fronts that expand outward. Webb resolved these jets with extraordinary clarity, showing their internal structure, the way they pulse in distinct bursts, and the complex pattern of the shock waves spreading through the surrounding material. One particular Herbig-Haro object, designated Herbig-Haro 211, was imaged by Webb and revealed a jet structure stretching roughly 2,000 astronomical units from end to end, with visible internal knots showing where repeated outburst events had stacked on top of each other. The source protostar is so young that it has not yet settled into a true star. it is still actively accreting material from the disk surrounding it. Watching a protostellar jet at this resolution gives researchers direct observational data on how young stars shape their immediate environments. The jets carry momentum outward, heating and compressing surrounding gas, influencing which parts of the cloud will collapse into more stars and which will be disrupted. Star formation is, in a sense, a self-regulating process, and Webb is showing us the machinery of that regulation in action. The young stars hidden inside the Carina Nebula's columns were expected to be there by theory. Seeing them directly, counting them, measuring their disks, changes theoretical inference into mapped reality. The number of young stellar objects Webb revealed in that region alone was higher than previous estimates had predicted. The violence of starbirth in these nurseries also shapes the surrounding cloud in ways that are only now becoming measurable. In one region that Webb revisited with high precision, the rate of erosion in the gas columns was faster than the best pre-Webb models had forecast. The pillars of creation are among the most recognizable structures in astronomy. First imaged by Hubble in 1995, they became an iconic symbol of star formation, columns of dark gas and dust rising from the Eagle Nebula, about 6,500 light-years away. Hubble revisited them in 2014 with improved instruments. Webb imaged them in 2022 with both near-infrared and mid-infrared cameras, and the results showed something the earlier images could not. In the near-infrared image, Webb resolved hundreds of newly formed stars embedded within and around the pillars, far more than were previously identified, along with the orange-red wavy edges of the columns, where active star formation is occurring. Stars at the edges of the pillars are producing intense ultraviolet radiation that heats and ionizes the gas around them, creating the characteristic glowing edges visible in Webb's image. The mid-infrared view revealed something separate and more alarming about the pillar's structure. The cold gas deep inside the columns showed up clearly, and the mapping of that gas allowed researchers to estimate the rate at which the outer layers of the pillars are being eroded by the radiation and stellar winds from massive nearby stars. That erosion rate came back higher than models built from previous data had predicted. The pillars will not survive indefinitely. Under current erosion rates, the columns are estimated to be destroyed on a timescale of roughly 3 million years. In astronomical terms, that is a relatively short life. What Webb's more precise measurements suggest is that the destruction timeline may be somewhat shorter than previous estimates had placed it. There is an important additional layer to the pillars' story. The light we see from them left 6,500 years ago. Some researchers, based on indirect evidence, have suggested that a supernova explosion may have already occurred close enough to the pillars to have destroyed or severely disrupted the columns. If that is correct, the pillars as we see them may no longer exist in their current form. Webb's image is a portrait of something that may already be gone. We are simply too far away to have received the news yet. That is a fact about cosmic distances that carries its own weight. The light travel delay means every deep image Webb takes is a history image. What appears as a present observation is actually a message from the past, sometimes the very deep past. When Webb images something 6,000 light-years away, with the precision of the pillars data, the science it reveals is real, but the scene it captures may have already changed in ways that will take millennia to reach us. The pillars also illustrated something Webb keeps demonstrating in different contexts. Objects and structures that were already studied in significant detail through previous generations of telescopes are revealing new measurable layers when viewed through Webb's instruments. The pillars were not a mystery before Webb. They were a known, mapped structure. Webb added quantitative precision about erosion rates, embedded stellar populations, and internal gas structure that changed their scientific value significantly. Each revisit of a known target through Webb produces new data. That pattern will continue as the telescope's observing program works through its target list, and some of the most dramatic revisits have taken place within our own solar system, where Webb has delivered images of familiar worlds that look fundamentally different when seen in infrared. When Voyager 2 flew past Neptune in August of 1989, it became the only spacecraft to ever visit the outermost known planet of our solar system. The flyby lasted hours. It revealed a dynamic world with active weather, dark storms, and, faintly, a ring system. Neptune's rings had been suspected from Earth-based observations of stellar occultations before the flyby, and Voyager 2 confirmed them. But the images were limited by the brief encounter and the technology of the time. After Voyager 2 left, Neptune's rings became almost invisible again. Ground-based telescopes, even large ones, struggled to pick them out against the glare of the planet. Hubble captured some ring data, but the rings remained poorly characterized. Webb imaged Neptune in 2002, and the rings came into sharp focus in a way they had not since Voyager 2. The image showed the complete ring system, including fainter diffuse rings that had barely been resolved before, with a clarity that surprised even the researchers who designed the observation. 7 of Neptune's moons were also visible in the same field. The rings are made of dust and small rocky particles. They are narrow and dark compared to Saturn's broad, bright ring system. Saturn's rings are icy and highly reflective. Neptune's rings contain a high proportion of dark material, possibly organic compounds, which makes them absorb light and appear dim in visible wavelengths. Infrared imaging gets around this because it detects the thermal and compositional properties of the material rather than relying on visible reflectivity. Webb also captured Neptune itself with unexpected crispness. The planet's atmospheric bands were visible, as were bright streaks corresponding to high-altitude clouds of methane ice crystals. These clouds had appeared in Hubble images before, but Webb resolved them with more detail than previous space-based observations. The north polar region of Neptune showed a hint of a bright glow in Webb's image, consistent with the known polar vortex, but visible in the infrared in a way that allowed researchers to probe its thermal structure more directly than Hubble's instruments permitted. For planetary scientists, Webb's Neptune image was both a demonstration of capability and the start of a new observational baseline. Voyager 2's flyby gave humanity one moment of close-up data. Hubble gave decades of periodic monitoring but limited ring resolution. Webb can now observe Neptune repeatedly, tracking changes in its ring structure and atmosphere over time. Any variation in ring brightness, any change in cloud distribution, any shift in the polar vortex can now be measured against a sharp, high-quality baseline. The rings of Neptune are also scientifically interesting because they are young. Ring systems in the outer solar system do not last forever. Gravitational dynamics and radiation pressure cause ring particles to slowly spiral inward or outward until the rings disperse. The fact that Neptune has rings at all means they are either continuously replenished from some source, possibly collisions between small moons, or they formed relatively recently in geological terms. Webb's clarity on those rings has reopened that longevity question with fresh data, and the same capacity that revealed Neptune's rings in such detail was about to be turned toward a star across a vast gulf of space, resolving a single point of light that turned out to be the most distant individual star ever identified. In April of 2022, a team analyzing data from the Hubble Space Telescope and the James Webb Space Telescope reported the detection of an individual star at a distance that had never before been achieved for a single stellar object. The star sits roughly 28 billion light-years away in terms of the present-day distance to where that galaxy sits, accounting for cosmic expansion. The light that reached the telescopes left when the universe was less than 1 billion years old. The star was named Earendel. Detecting an individual star at that distance is, under normal circumstances, completely impossible. Stars are tiny. Even the most powerful telescopes cannot resolve individual stars beyond our local group of galaxies under ordinary conditions. Earendel was only detectable because of a phenomenon called gravitational lensing. A massive galaxy cluster called WHL 0137 sits between us and Earendel. That cluster contains so much mass that its gravity bends and distorts the light passing through it from more distant objects behind it. In specific geometrical alignments, this bending amplifies the light from a background source by enormous factors, functioning as a natural cosmic magnifying glass. Earendel happened to lie almost exactly on a critical lensing curve where the amplification factor reached thousands. A single star, at a distance where we could never otherwise detect it, was temporarily made bright enough to be measured. Webb confirmed and detailed the observation that Hubble had initially spotted. Webb's infrared sensitivity allowed researchers to measure the color and temperature of Earendele's light more precisely. The data suggested that Earendel is a massive, hot, blue star, likely many times more luminous than our own stellar neighbor, and several times more massive than any star we can observe in our local stellar neighborhood, without lensing assistance. Stars of that mass and temperature do not live long. They burn intensely and destroy themselves in supernova explosions within a few million years. Earendel no longer exists. The star we are observing in these images ran through its entire life cycle billions of years ago. What the telescope is seeing is the ancient light from a stellar life that ended long before Earth formed. The significance of Earendel extends beyond the single detection. It demonstrated that gravitational lensing combined with Webb's sensitivity can push the boundary of individual stellar observation into the first billion years of cosmic history, a regime where astronomers previously had access only to the integrated light of entire galaxies, never individual components within them. Webb has since observed additional lens sources near Earendel, including what appears to be a compact cluster of young stars in the same background galaxy, further demonstrating that this lensing geometry can be used as a tool rather than a lucky singular event. The question immediately raised by finding such a massive luminous star this deep in cosmic time is whether stars in the early universe routinely formed with sizes and temperatures that are rare in the modern universe. Early stars formed from gas with almost none of the heavy elements that modern star formation involves, and that change in chemistry may have produced a dramatically different stellar population. Exploring that difference is one of Webb's core science goals, and it requires looking even farther back and even more carefully at the earliest light the universe produced. The oldest stars we can study in detail are the ones in our own galaxy and nearby galaxies that formed early and are still present. These ancient stars show a signature that astronomers call metal poor. In astronomy, any element heavier than helium counts as a metal, and the oldest surviving stars carry very low concentrations of these heavier elements. That pattern makes sense. The universe began with almost only hydrogen and helium. Heavier elements were built inside stars and scattered by supernova explosions. The first generation of stars formed before any of that enrichment had happened. Astronomers call this theoretical first generation population 3 stars. They have never been directly observed. The reason is straightforward. They formed in the first hundreds of millions of years of the universe, burned through their fuel rapidly because of their enormous mass, and died in supernova explosions so powerful they scattered heavy elements across entire proto-galaxies. There are almost certainly no surviving population 3 stars anywhere in the observable universe. They destroyed themselves long ago. Webb cannot directly image a population 3 star, for the same reason Earendel required a gravitational lens to detect. Individual stars at that distance and era are far too faint even for Webb's sensitivity. But Webb can look for signatures of population 3 star formation in the chemical makeup of early galaxies. Evidence is accumulating, though still tentative and actively debated, that some of the earliest galaxies Webb can spectroscopically analyze carry chemical fingerprints consistent with having been seeded by population 3 stellar explosions. The specific ratios of nitrogen and carbon found in one early galaxy published in 2002 led a research team to suggest that extremely massive stars, several hundred times the mass of a typical modern star, had exploded as what are called pair instability supernovae and imprinted those ratios into the surrounding gas. A pair instability supernova happens when a star is so massive that the gamma rays produced in its core begin converting into electron-positron pairs rather than supporting the star's weight. The core loses pressure support and collapses explosively. The explosion is so energetic that it can leave no remnant at all, producing no neutron star or black hole, just a cloud of chemically enriched gas expanding outward at extreme velocity. If early galaxies were seeded by population 3 pair instability supernovae, the chemical enrichment of the universe happened in a single violent generation of monstrous stars, before any smaller, longer-lived stars even had the chance to form. The pattern of heavy elements we see today, in even the most ancient surviving stars, would carry the fingerprint of those first explosions. This remains a theoretical framework, with supporting but not conclusive evidence. Webb is adding data points. Each high redshift galaxy whose chemical composition can be measured gives researchers another piece of the population 3 puzzle, narrowing the range of possibilities for what the first stellar generation actually looked like. And somewhere at the absolute edge of what Webb can detect, there exists an object whose redshift pushes it to within the first 100 million years of the universe, so far back that even its basic nature remains uncertain. That object, and what it might mean for everything we have built in this script so far, waits in the next chapter. Webb's detection limit is not a sharp wall. It is a gradient, a region where signals grow fainter, uncertainties grow larger, and the interpretation of data requires more caution. At the deepest end of that gradient, researchers have found objects whose light carries such extreme redshift that placing them in cosmic time pushes against the very boundary of what current physics predicts should be detectable. One such object emerged from Webb's deep field data in 2203. A candidate galaxy, still under active analysis at the time of its initial publication, carried a photometric redshift estimate, placing it at a distance corresponding to when the universe was roughly 180 million years old. If confirmed spectroscopically, it would sit among the earliest structures ever detected. Some candidates in Webb's deep fields have pushed even closer to the first 100 million years, though none of those extreme cases has yet received the gold standard spectroscopic confirmation that fully locks in a distance measurement. Photometric redshift means the distance was inferred from how the object's brightness drops off across different wavelength filters, rather than from a direct measurement of spectral lines. It is a reliable technique, but carries larger uncertainties than spectroscopy. A photometric redshift estimate can shift when full spectroscopic follow-up is completed. Some objects that initially appeared at record distances have been revised to closer, more modest redshifts after deeper observation. Scientists working in this field are transparent about this, and the most careful publications flag their candidate redshifts clearly as awaiting confirmation. What makes these extreme candidates worth attention even before confirmation is the pattern they contribute to. Webb is consistently finding galaxies, confirmed and candidate, at distances that compress the timeline of early cosmic structure formation. Each new confirmed high redshift galaxy adds pressure to models that were built when the deepest confirmed objects were at somewhat lower redshifts. The universe at 100 to 200 million years old was a specific physical environment. Gas was cooling from the extreme temperatures of the early cosmos. Dark matter halos were only beginning to collapse into the first gravitational wells where gas could concentrate. The first stars, if the population 3 framework is correct, were just igniting inside those halos. Finding a galaxy-scale object in that window would mean that matter organized from diffuse gas into a structured system of millions of stars with extraordinary speed. Every aspect of what Webb finds at these extreme distances feeds back into a central question that the telescope has been sharpening since its first science images arrived. The models built to describe the universe from its first moments to today rely on known physics: gravity, dark matter, dark energy, nuclear physics, the behavior of gas under pressure and heat. Those models have been tested against observations for decades and have worked remarkably well across most of the timeline. At the earliest epochs Webb can reach, those models keep running slightly behind reality. The universe at its youngest appears to have moved faster, organized sooner, and built larger structures earlier than the models predicted. Each anomaly is, individually, within the range of what adjustments to model parameters might explain. Together, across multiple independent lines of evidence, from Webb's first 2 years of operation, they point towards something in our picture of the early universe that may be incomplete. The object at the edge of Webb's range may or may not survive full spectroscopic confirmation at its initial estimated distance. What it represents, regardless of its final confirmed location in cosmic time, is the outermost data point in a series of findings that all lean in the same direction. And that direction is becoming harder to look away from. Most of what Webb has revealed involves the universe at its largest scales: galaxies, galaxy clusters, cosmic structure across billions of light years. But Webb also turns toward compact, violent events in the modern universe. And in one targeted observation of a binary star system, it caught something that physicists had modeled in detail, but rarely witnessed directly with this level of clarity. A binary star system is two stars orbiting each other. When one of those stars reaches the end of its life and collapses into a white dwarf, the system enters a new phase. A white dwarf is the dense, cooling remnant of a star that was not massive enough to become a neutron star or a black hole. It is roughly the size of Earth, but contains a mass comparable to a full star, compressed until electrons themselves resist further compression. The surface gravity of a white dwarf is enormous. If the white dwarf orbits close enough to its companion star, that gravity begins pulling material off the companion's outer layers. The stolen gas flows across the gravitational boundary between the two stars and accumulates on the white dwarf's surface. As that layer of hydrogen and helium builds up over time, the pressure and temperature at the base of the layer increase. Eventually, the accumulated gas reaches the threshold for runaway nuclear fusion, and it ignites all at once across the white dwarf's surface in a thermonuclear explosion visible across light years. This event is called a classical nova. The white dwarf survives it. The explosion blasts the accumulated shell of material away, and over time, mass transfer from the companion resumes. The cycle can repeat. Webb observed the nova system known as RS Ophiuchi during one of its outbursts, along with coordinated observations from other telescopes. RS Ophiuchi is a well-studied recurrent nova that undergoes these explosions roughly every 15 to 20 years. Its most recent major outburst occurred in 2002. Webb's infrared observations captured the expanding shell of ejected material and the thermal properties of the nova remnant as it cooled and thinned over time. The data allowed researchers to probe the geometry and composition of the ejected material with a precision that ground-based infrared observations of previous outbursts had not achieved. The interaction between the expanding nova shell and the dense wind previously shed by the companion giant star created a complex, shocked region whose temperature and density profile Webb could map. Recurrent novae like RS Ophiuchi are also scientifically significant for a reason that connects to the largest scales of cosmology. Under specific conditions, if a white dwarf in a binary system accumulates enough mass over time without fully expelling it through nova outbursts, it can eventually reach a critical mass threshold and undergo a far more violent event, a type 1A supernova, an explosion so consistent in its brightness that astronomers use it as a standard reference candle for measuring cosmic distances. Understanding exactly how mass accumulates in systems like RS Ophiuchi and whether the white dwarf is growing or shrinking with each nova cycle connects binary star physics directly to the distance measurements at the foundation of cosmology. The Hubble tension itself depends on calibrated supernova distances. Webb's ability to probe the mass transfer dynamics in these systems adds precision to that chain of measurement. The Milky Way currently forms between 1 and 3 new stars per year. That rate is low by the standards of cosmic history. Our galaxy has aged past its most productive era. The gas reservoirs that once fueled intense star formation have largely been consumed, expelled, or heated to the point where they can no longer condense into new stars. In the early universe, star formation rates were dramatically higher. Galaxies at high redshift, when the universe was between 1 and 3 billion years old, were producing stars at rates that dwarf anything observed in the modern cosmos. Some of these galaxies, called starburst galaxies, were forming stars at rates of hundreds to over 1,000 times the pace of the current Milky Way. Webb has observed several of these extreme starburst systems in detail, and one finding that keeps emerging from that data is how the intense star formation drives massive outflows of gas from these galaxies. When thousands of massive stars form in a compact region and then explode as supernovae in rapid succession, the combined energy of those explosions creates a superwind, a large-scale outflow of gas and dust, moving at hundreds of miles per second away from the galaxy. These galactic winds are a critical mechanism in galaxy evolution. They remove gas that would otherwise fuel more star formation, self-regulating the starburst and eventually quenching it. They also enrich the space between galaxies with heavy elements, seeding the intergalactic medium with the chemical products of stellar nucleosynthesis. Every galaxy in the modern universe, including our own, has been shaped partly by outflows from earlier epochs that redistributed material across enormous scales. Webb has mapped these outflows in early starburst galaxies with a level of spectroscopic detail that allows researchers to measure their speed, their chemical composition, and the amount of mass being ejected per year. In some systems, the outflow rate is comparable to or exceeds the star formation rate, meaning the galaxy is losing gas as fast as it is converting it into stars. That balance determines how long the starburst phase lasts before the galaxy exhausts or expels its fuel. One starburst galaxy, Webb, examined in a deep field, sits at a redshift placing it in the universe's second billion years. Its estimated star formation rate exceeded 500 times that of the present-day Milky Way. The outflow Webb spectroscopy detected in the same system was carrying mass away from the galaxy at a rate that, if sustained, would exhaust its visible gas reservoir within a few 100 million years. That is a compressed life cycle for a galaxy. Build enormous stellar mass quickly, drive powerful winds that strip the remaining gas, and arrive at a quenched state that would look, to a later observer, like a massive red, dead galaxy that somehow completed its entire arc too fast for standard models to accommodate. The connection to the quenched galaxies Webb has found at extreme redshift, described earlier in this script, runs directly through these starburst outflow observations. Dark matter is the most abundant form of matter in the universe, and it has never been directly detected. It does not emit light. It does not interact with the electromagnetic force at all, as far as we can measure. Its existence is inferred entirely from its gravitational effects on visible matter. Galaxies rotate in ways they could not sustain if only their visible stars and gas provided the gravity. Galaxy clusters bend light more strongly than their visible mass predicts. The large-scale structure of the cosmos follows a pattern that matches simulations only when dark matter is included. Webb has not detected dark matter directly. No telescope can. But Webb has produced gravitational lensing observations of sufficient precision that researchers can map where dark matter must be concentrated in order to produce the lensing patterns Webb measures. In clusters of galaxies Webb has observed, the distribution of lensed background sources, the arcs and distorted images of distant galaxies bent by the cluster's gravity, allows researchers to reconstruct the full mass distribution of the cluster, including the invisible dark matter component. These mass maps reveal that dark matter in clusters does not simply follow the distribution of visible galaxies. It forms extended, smooth halos that surround and connect the visible galaxy members. Webb's lensing maps have achieved finer spatial resolution than previous instruments, allowing researchers to probe dark matter distribution on smaller scales within clusters. One active area of investigation involves the central regions of clusters where dark matter density reaches its peak. The exact shape of that central density profile, whether it rises steeply toward the center or flattens into a core, carries information about the nature of dark matter particles themselves. Different dark matter candidates produce different predicted profiles. Webb is generating data that can begin to distinguish between them. In several clusters, Webb has studied in detail. The lensing maps have revealed substructure in the dark matter distribution that corresponds to smaller galaxy groups being absorbed into the larger cluster. These infalling groups bring their own dark matter halos with them, and the halos take time to merge and relax into the cluster's overall structure after the visible galaxies have already blended together. Webb's precision allows researchers to catch this lag, mapping places where the dark matter distribution still reflects a merger that visually appears complete. There is also a connection between Webb's early galaxy findings and dark matter theory. The massive, early, well-organized galaxies Webb has found pose a challenge not just to star formation models, but to the dark matter model itself. Standard cold dark matter theory predicts how quickly dark matter halos should collapse and grow at each epoch. If galaxies are assembling faster than those halos can grow, either the galaxy formation efficiency is operating outside expected parameters, or the dark matter model needs adjustment. Some researchers have explored alternative dark matter models, including warm dark matter, in which particles move fast enough to smooth out small-scale structure, and self-interacting dark matter, in which particles can exchange momentum with each other in ways that alter the density profiles Webb's lensing observations are now measuring. These are open theoretical questions. The answers will come partly from Webb's continued lensing observations and partly from laboratory experiments searching for dark matter particles directly. Among all the planets Webb has studied in detail, the most scientifically loaded target class is the rocky terrestrial worlds. Gas giants like WASP 39b and subneptunes like GJ1214b gave Webb its early atmospheric chemistry triumphs. But the ultimate goal, the one that drives the deepest investment in planetary science, is to characterize the atmosphere of a rocky planet roughly the size and mass of Earth, orbiting in a star's habitable zone. Webb is working toward that goal, and the progress is real but comes with honest caveats. Rocky planets are far harder atmospheric targets than gas giants. Their atmospheres are thinner. The transit signal, the tiny dimming of starlight as the planet crosses in front of its star, carries a much smaller atmospheric component when the planet itself is small. The signal-to-noise challenge is severe. Webb has already produced the first tentative thermal emission measurements of rocky exoplanets, as covered through the TRAPPIST system earlier. In 2004, researchers using Webb published a measurement of the thermal emission from the planet TRAPPIST-1c that constrained its surface temperature with enough precision to argue against a thick carbon dioxide atmosphere. That result required multiple transits stacked together over many hours of observation time. The same technique, applied to a planet with a confirmed atmosphere, could in principle detect the chemical fingerprints of that atmosphere over many combined transit observations. Webb sensitivity puts this within reach for certain rocky planet targets, specifically those orbiting nearby dim stars, where the planet-to-star size ratio is more favorable. One rocky world that represents a compelling near-term target is LHS 1140b, a super-Earth about 1.5 times Earth's radius, orbiting a small red dwarf star about 50 light-years away. It sits squarely in the habitable zone of its star. Early analyses from pre-Webb telescopes suggested it might retain an atmosphere. Webb observations of this system are ongoing, and researchers involved have indicated the data quality is sufficient to eventually either detect or rule out certain atmospheric scenarios. The detection of a confirmed stable atmosphere on a rocky habitable zone planet would be a significant result. It would establish that such atmospheres can survive the radiation environment of a red dwarf host star, at least in some configurations, and would open the path towards searching for molecular biosignatures in that atmosphere with continued observations. The reality is that Webb, even with its extraordinary capability, will likely require hundreds of transit observations of the most promising rocky planets to build up enough signal to make confident atmospheric detections. That observing time competes with every other science goal the telescope carries. Decisions about where to invest Webb's limited lifetime are ongoing and involve real trade-offs across the astronomy community. Reading the chemistry of an exoplanet atmosphere is one thing. Mapping how heat moves around an entire planet is another. For years, researchers had theoretical models of how energy redistributes itself across gas giant exoplanets that orbit close to their stars. But testing those models required thermal measurements precise enough to track temperature differences between the day side and the night side of a distant world. Webb provided those measurements. The target was a hot Jupiter, a gas giant orbiting so close to its star that one side permanently faces the star and the other permanently faces away. This locked rotation, called tidal locking, means the day side absorbs intense stellar radiation continuously, while the night side stays in permanent darkness. The question is how efficiently the planet's atmosphere transports that heat from the blazing day side to the cold night side. Efficient heat transport would produce a planet with a relatively modest temperature difference between its two hemispheres. Inefficient transport would leave the day side extremely hot and the night side extremely cold. Webb measured the full thermal phase curve of a hot Jupiter, tracking the planet's infrared brightness continuously as it orbited its star over roughly 40 hours. As different parts of the planet rotated into and out of our line of sight, the changing brightness told researchers the temperature of each region they were observing. The resulting map showed a dayside hotspot that was offset from the point directly beneath the star, shifted slightly in the direction of the planet's orbital motion. That offset indicates that strong atmospheric winds were carrying heat forward, distributing it ahead of where the star's energy was being deposited. The night side temperature, even with that atmospheric redistribution, remained dramatically colder. The temperature contrast across this planet reached into the range of several hundred degrees, confirming that even with strong winds, the extreme proximity to the star creates thermal gradients far beyond anything in our solar system. This kind of thermal mapping provides a direct test of atmospheric circulation models. The planet's specific temperature distribution was then compared against simulations, and the comparison revealed areas where the models performed well and areas where the observed winds and temperature structure deviated from predictions. Those deviations guide theorists toward more accurate frameworks. For the long-term goal of understanding habitability, thermal circulation matters beyond gas giants. Rocky planets in habitable zones also experience varying degrees of heat redistribution, depending on whether they are tidally locked, how thick their atmospheres are, and what their surface conditions look like. The techniques refined on hot Jupiters with Webb are being adapted for application to smaller, cooler targets as the telescope's observing program expands. The ability to map temperature distributions across entire planetary hemispheres from over 1,000 light-years away would have been a thought experiment a decade ago. Webb turned it into a regular observational technique, and the discipline of comparative exoplanet meteorology is building from that foundation. Space between galaxies is not empty. It contains gas, mostly hydrogen and helium, traces of heavier elements, and a class of molecules that, when Webb first confirmed their presence in intergalactic environments, surprised researchers who had expected them only in specific protected locations. Polycyclic aromatic hydrocarbons are large carbon-based molecules, ring-shaped structures made of linked carbon and hydrogen atoms. They are everywhere in space, embedded in dust clouds, drifting through interstellar gas, and produced in abundance by the carbon-rich outflows of dying giant stars. On Earth, polycyclic aromatic hydrocarbons form in combustion, in car exhaust, in wood smoke, in grilled food. In space, they appear wherever carbon chemistry operates at scale. What Webb revealed in detailed observations of starburst galaxies and their surrounding environments is that polycyclic aromatic hydrocarbons were being pushed out of galaxies by the superwinds those galaxies generate, transported into the intergalactic medium at distances far from any star or stellar nursery. The infrared signature of these molecules was detectable in regions where the density of matter was very low, far from the dense star-forming clouds where they are typically found. This matters for understanding the chemical seeding of the universe. Every galaxy that drives a powerful outflow is distributing its chemical products across the surrounding space. Those products include the heavier elements produced by stellar nucleosynthesis, the dust grains that form around dying stars, and now confirmed, complex organic molecules like polycyclic aromatic hydrocarbons. When that enriched gas eventually falls back into galaxies, gets swept up in later generations of galaxy formation, or mixes with the gas clouds that form new stars, it carries that chemical inheritance with it. The polycyclic aromatic hydrocarbons, in particular, are thought to play a role in the early stages of interstellar chemistry that can eventually lead to more complex organic molecules. The connection between intergalactic chemistry and the origin of organic compounds in planetary systems is a long chain. But Webb is demonstrating that the chain starts earlier and extends farther than previously measured. The raw chemical ingredients for complex molecular chemistry are being distributed across cosmic scales by the same outflows that shape galaxy evolution. Webb's mid-infrared spectrograph is particularly well suited for detecting polycyclic aromatic hydrocarbons because their strongest spectral features fall in the mid-infrared wavelength range, exactly where Webb's mid-infrared instrument operates at its highest sensitivity. Hubble could not access this wavelength range at all. Spitzer could, but at far lower resolution and sensitivity. Webb can now map the distribution of these molecules across the extended environments of galaxies at significant redshift, building the first real picture of how carbon chemistry distributes itself on cosmic scales. Stephan's quintet is a group of 5 galaxies so close together in the sky that they appear as a single crowded region through small telescopes. 4 of them are genuinely associated with each other, sitting roughly 290 million light-years away, and locked in a slow gravitational dance that has been playing out for billions of years. The 5th, Positioned in the foreground is an unrelated galaxy about 40 million light-years away that happens to appear nearby in projection. Webb released a mosaic image of Stephan's quintet that was, at the time of its release in July 2002, the largest image Webb had produced. It covered an area of sky equivalent to roughly 1/5 of the full moon's diameter, but revealed detail at a resolution and depth that transformed the quintet from a known curiosity into a laboratory for studying galaxy interactions in real time. The most scientifically significant structure in Webb's quintet image is a massive shockwave running through the intragroup gas. One of the four physically associated galaxies is currently plunging into the others at roughly 2 million miles per hour. As it passes through the hot, diffuse gas filling the space between the other galaxies, it drives a shockwave that heats that gas to millions of degrees and generates powerful emissions. Webb captured the spatial structure of this shock across the entire quintet, mapping how the kinetic energy of the infalling galaxy converts into heat and turbulence in the surrounding medium. Inside the shocked region, Webb found something unexpected: pockets of warm molecular hydrogen gas mixed into the same space where the shock heating is occurring. Molecular hydrogen normally requires cold, dense conditions. Finding it within a violently shocked region suggests that the turbulence is not uniformly destructive, that pockets of cooler, denser gas can survive or rapidly reform, even in an environment where the overall conditions are extreme. Webb's mid-infrared imaging also revealed the detailed structure of the active galactic nucleus in one of the quintet's members, a galaxy called NGC 7317. The core of this galaxy contains an actively feeding black hole, and Webb's infrared view cut through the obscuring dust around that core to reveal the thermal structure of the surrounding material being dragged inward. The quintet is a preview of interactions that will play out across the universe on larger scales. When galaxy clusters merge, the physics occurring in the quintet's compressed environment, shock heating, turbulent gas mixing, nuclear activation, play out at scales thousands of times larger. Webb's ability to map all of these processes simultaneously in one compact, well-studied system gives researchers a template they can apply to interpreting the more distant, less resolved systems that Webb observes across cosmic time. In 1995, the Hubble Space Telescope pointed at a tiny blank patch of sky and held its gaze for 10 consecutive days. The resulting image revealed 3,000 galaxies in a region of sky smaller than a grain of sand held at arm's length. It was called the Hubble Deep Field, and it changed our understanding of how many galaxies the universe contains. Webb produced its own deep field image in the first week of science operations, and released it on July 11, 2210, as the first full-color science image from the telescope. The region covered was slightly smaller than the Hubble Deep Field, but the depth, the ability to detect faint, distant objects, exceeded Hubble's by a significant margin due to Webb's larger mirror and infrared sensitivity. Thousands of galaxies filled the image. Many of them appeared in shapes and configurations that Hubble's deeper exposures of other fields had already established as the standard population of distant galaxies. Several, however, appeared at distances and redshifts, placing them significantly beyond the range Hubble could access effectively. Webb's deep field image became an instant resource for multiple research teams who began analyzing the population statistics of distant galaxies, the number counts at different redshifts, the morphologies, the color distributions, and the clustering patterns. One of the things the image made immediately clear was the abundance of gravitational lensing events visible in the field. Multiple background galaxies had their light bent into arcs by the gravity of foreground galaxy clusters visible in the same frame. Each arc represents a natural cosmic amplification, allowing Webb to study the lensed background galaxy at a level of detail that would otherwise be impossible. Webb's deep field thus works simultaneously as a direct survey of galaxy populations and as a gravitational lens survey, two different science modes in the same image. Counting galaxies in the deep field also feeds into estimates of the total number of galaxies in the observable universe. Earlier Hubble-based estimates placed that number at roughly 2 trillion, far more than the few hundred billion suggested by earlier surveys. Webb's deeper reach does not fundamentally overturn this estimate, but it adds precision at the high redshift end of the distribution. refining our understanding of how the galaxy population thins out as you approach the earliest epochs. Each galaxy in the deep field is a separate island of hundreds of billions of stars, with its own history of formation, merging, star formation, and quenching. Extracting that information from each galaxy individually requires spectroscopic follow-up. Webb's spectroscopic instruments are being used to measure redshifts and chemical compositions for selected targets within and near the deep field, building a three-dimensional picture of how those galaxies are distributed in space and how they are connected through the large-scale structure of the cosmic web. The deep field image is both a result and a starting point. The science extracted from it will continue accumulating for years. The large-scale structure of the universe is not a random scatter of galaxies. Gravity has organized matter over billions of years into a vast network of filaments, sheets, and nodes, separated by enormous empty regions. Galaxies cluster along the filaments. At the intersections of filaments, the densest galaxy clusters sit like knots in a net. Between the filaments, stretching across tens of millions of light years, lie voids, regions nearly empty of galaxies and gas. This structure, called the cosmic web, was predicted by simulations of how dark matter collapses and organizes under gravity. When simulations using cold dark matter were run forward from the early universe to the present day, they produced a filamentary network that matched the observed distribution of galaxies remarkably well. The cosmic web became one of the strongest arguments for cold dark matter as the dominant form of matter in the universe. Webb is now observing the cosmic web at redshifts high enough that the filamentary structure was still assembling. Observations of galaxy protoclusters, dense regions in the early universe that were in the process of collapsing into the large clusters visible in the modern universe, have been carried out with Webb's spectroscopic instruments. By mapping the redshifts of galaxies across a field and looking for groups of galaxies at the same distance, researchers can identify where the large-scale structure was concentrating in the early universe. In 2023, a team using Webb identified an extended structure of galaxies at a redshift corresponding to roughly 800 million years after the Big Bang, with multiple galaxy groups distributed across a region spanning tens of millions of light-years. The galaxies within this structure showed signs of enhanced star formation relative to galaxies at similar redshifts in less overdense environments, consistent with the idea that the dense filamentary nodes of the cosmic web were preferential sites for accelerated galaxy growth. The filaments themselves, the thin threads of gas connecting galaxy clusters, remain difficult to detect directly even with Webb, because the gas within them is sparse and diffuse. But the galaxies strung along those filaments are visible, and their distribution traces the Webb's architecture. Webb's ability to measure spectroscopic redshifts for large numbers of faint galaxies is building three-dimensional maps of these early large-scale structures with a precision that previous surveys of the high redshift universe could not achieve. Every map of the early cosmic web that Webb produces is a test of the cold dark matter model. The filament positions, the void sizes, and the cluster masses at each epoch should match the model's predictions if cold dark matter is the correct description of the universe's invisible scaffolding. So far, the broad agreement holds. But some of the dense, massive structures Webb finds at the highest redshifts strain the expected formation timeline, consistent with the pattern of early universe anomalies that runs throughout the telescope's findings. Every large galaxy in the modern universe contains a supermassive black hole at its center. The Milky Way's central black hole carries a mass of roughly 4 million times that of a typical star. Larger galaxies host proportionately larger central black holes. The relationship between a galaxy's mass and the mass of its central black hole is remarkably consistent across the modern universe, suggesting that galaxies and their central black holes grew together, each influencing the other's development. How black holes reach their enormous modern masses is one of the deepest unresolved problems in astrophysics. Black holes grow by consuming gas and merging with other black holes. But there is a speed limit. When a black hole feeds too aggressively, the radiation from the infalling gas becomes so intense that it pushes the surrounding gas away, limiting how fast the black hole can consume material. This limit is called the Eddington rate. Sustained growth at the Eddington rate for millions of years can build a large black hole. but building a black hole of several billion solar masses within the first billion years of the universe requires either starting from a very large seed, sustaining Eddington, or super Eddington growth for extended periods, or both. Webb has detected active galactic nuclei, which are the bright signatures of actively feeding black holes, at redshifts corresponding to the universe's first billion years. Some of these early active nuclei are astonishingly luminous, implying black holes already hundreds of millions of times more massive than a typical star, feeding at high rates, at an age when the models say they should barely have had time to form. A published finding in 2023, using Webb data, identified several compact red sources at high redshift that appear to be active black holes embedded in host galaxies. These so-called little red dots were initially puzzling because their brightness and compactness did not fit cleanly into either the galaxy or active nucleus categories the field had established. Ongoing analysis has converged on the interpretation that many of them are actively feeding black holes in the early universe, some potentially growing at rates that challenge standard Eddington limited growth models. The implication is that whatever seeded these black holes in the early universe, whether massive population 3 stellar remnants, direct collapse of enormous gas clouds, or some other mechanism, was efficient enough to produce large black holes rapidly, and that those black holes grew even faster than the standard model of accretion allows. This feeds directly back into the early galaxy mass problem. The same galaxies Webb finds too massive, too soon may also harbor black holes that are too massive too soon, suggesting the entire system of galaxy plus black hole coevolution was running at a pace that current theory has not fully captured. Dust in space is nothing like household dust. Cosmic dust particles are microscopic, measured in fractions of a micron, and they are made of silicates and carbon compounds forged inside dying stars and distributed through stellar winds and supernova explosions. Despite their tiny size, dust grains play an enormous role in cosmic chemistry. They are the surfaces on which simple molecules combine into more complex ones. They shield cold gas clouds from radiation, allowing temperatures to drop low enough for molecules to form. They are the raw material from which planet surfaces ultimately derive. One of the persistent puzzles of the early universe was how so much dust could exist at high redshift. Dust is built from heavy elements produced inside stars. The first stars to form were made of almost pure hydrogen and helium. For dust to be abundant in the early universe, massive stars had to form, live short lives, explode, and distribute their heavy elements fast enough for a significant population of dust grains to accumulate within the first billion years of cosmic time. Webb is measuring the dust content of high redshift galaxies with far greater precision than previous instruments, and the results confirm that some early galaxies contained enormous quantities of dust within the first billion to 2 billion years of cosmic time. This dust abundance implies that the stellar population driving that enrichment was forming and dying at extremely high rates. In some of the early starburst galaxies Webb has observed, the star formation is so heavily embedded in dust that significant fractions of the ultraviolet and visible light from young stars are completely absorbed by the dust and re-radiated as infrared light. Webb's infrared sensitivity makes it ideal for detecting these dust-obscured starbursts, which were partially invisible to Hubble. Some of the most intense star formation in the early universe was essentially hidden from optical telescopes, and Webb is now mapping it directly. The dust-obscured star formation rates Webb detects in some high redshift galaxies add to the total inferred star formation history of the early universe. When these previously hidden contributions are included, the total amount of stellar mass assembled in the first few billion years of cosmic time increases beyond what optical surveys alone had suggested. That upward revision in early stellar mass production is another thread in the same pattern that Webb keeps pulling. Every anomaly Webb has revealed across its first 2 years of science operations sits within a broader context that physicists call the Standard Model of Cosmology. This model, built over decades from observations of the cosmic microwave background, galaxy surveys, supernova distance measurements, and gravitational lensing, describes a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It has been tested more rigorously than almost any framework in science. It has survived challenges from multiple independent measurement methods, Its predictions have been confirmed by surveys covering billions of light years. The Standard Model is, by most measures, one of the most successful theories in the history of physics. And yet it has cracks. The Hubble tension is real and has not gone away with Webb's more precise measurements. The early galaxy mass problem is real and has not been explained by minor parameter adjustments. The early disk galaxy problem is real. The quenched early galaxies are real. The early black hole mass problem is real. Each of these anomalies is, taken alone, potentially resolvable through adjustments within the Standard Model's parameter space. Together, consistently pointing in the same direction, they constitute a pressure that the field cannot ignore. Cosmologists are clear that the Standard Model is not broken. The evidence for dark matter and dark energy remains strong. The overall structure of the cosmic web matches simulations. The agreement between the cosmic microwave background predictions and large-scale structure observations is excellent across most scales and most epochs. What Webb is doing is finding the places where the agreement frays at the edges, the very early universe, the fastest-growing galaxies, the most massive early structures. These are the extreme corners of the parameter space where the model's predictions face the most tension with observation. The scientific community's response has been active and productive. New theoretical frameworks are being tested, including modifications to dark energy, changes to the dark matter model, revisions to the feedback physics in galaxy formation simulations, and new treatments of how the first black holes formed and grew. None of these has yet emerged as a clear winner. The competition between explanations is ongoing. What is settled is that Webb has changed the resolution at which these questions can be asked. The anomalies are now measurable with the precision needed to distinguish between competing models. In the years ahead, as Webb accumulates more data and more spectroscopic confirmations, the theories that survive will be the ones that can account for all of what the telescope has seen. There is a specific, uncomfortable way to summarize Webb's 2 years of science. Take the standard cosmological model. Run it forward from the Big Bang. At each epoch, ask what the model predicts you should find if you look at the universe with a sufficiently powerful telescope. Then, compare those predictions to what Webb actually measures. In the modern universe, the agreement is good. Galaxy shapes, sizes, clustering patterns, the rate of star formation in nearby galaxies, the distribution of atomic hydrogen gas, the properties of galaxy clusters. The model handles these well. Push the comparison back to the first 2 billion years, and the agreement becomes messier. More massive galaxies than predicted, more organized structures than predicted, more dust than predicted, more luminous black holes than predicted, star formation switched off earlier than predicted, and an expansion rate, measured from nearby objects, that disagrees with what the model predicts based on the cosmic microwave background. Webb did not create these tensions. The early galaxy mass problem was already being discussed from ground-based surveys before Webb launched. The Hubble tension predates Webb, but Webb sharpened both of them, removed measurement uncertainties that had allowed some researchers to hold out hope they would disappear with better data, and added new, more precise versions of the same pattern in the early universe disk galaxy observations and the early quenching detections. The scientific process responding to this is exactly what physics is designed to do. Theorists are proposing modifications. Observers are designing tests to distinguish between those modifications. The data from Webb is being analyzed by large independent teams who check each other's results. The process is slow by the standards of social media, where a preprint becomes a headline within hours. But it is working. Systematic errors are being hunted and addressed. Alternative explanations are being evaluated. What the pattern suggests, when you step back from any single anomaly and look at the full collection, is that something about the very early universe allowed it to assemble faster, more efficiently, and more organized than our current picture of physics and dark matter and dark energy predicts. Whether that something is a new physical ingredient, an incomplete understanding of how dark matter behaves on small scales, an unexpected efficiency in early star and black hole formation, or something else that no one has yet proposed, remains an open question. An honest, productive, genuinely open question being worked on by large numbers of serious researchers. There is a boundary in cosmic time called the epoch of reionization. In the first few 100,000 years after the Big Bang, the universe was too hot for electrons to bind to atomic nuclei. Everything was a plasma, a fog of charged particles through which light could not travel freely. Then, the universe cooled enough for neutral atoms to form. Light could finally travel. The cosmic microwave background we detect today is the light that escaped at that moment. For hundreds of millions of years after that, the universe was filled with neutral hydrogen gas and was, for all practical purposes, dark. No stars, no galaxies, no sources of visible light. Just cooling gas drifting through expanding space, slowly falling into the gravitational wells of dark matter halos. Then the first stars ignited. Their ultraviolet radiation began stripping electrons from the surrounding hydrogen gas, a process called reionization. Over hundreds of millions of years, this reionization spread outward from the first galaxies, like bubbles expanding through the neutral fog, eventually merging and clearing the universe into the largely transparent state it occupies today. Webb is directly observing galaxies that existed during the epoch of reionization. The light from these galaxies, heavily redshifted, arrives in the infrared. Their spectra carry the imprint of the neutral hydrogen that surrounded them when that light was emitted. By measuring the strength of the neutral hydrogen absorption in different galaxies at different redshifts, researchers can trace the progress of reionization across cosmic time. What Webb is revealing is that reionization was patchy and somewhat more complete in certain regions earlier than models had suggested. Some galaxies deep in the reionization epoch show surprisingly clean spectra, indicating they resided in regions where the surrounding neutral hydrogen had already been cleared. That patchiness implies that reionization proceeded differently in overdense and underdense regions of the early universe, with the first galaxies in dense filaments driving faster local reionization than isolated galaxies in less dense environments. The galaxies driving reionization were small, numerous, and energetic. They were not the massive luminous objects Webb finds at the high end of the early galaxy mass distribution. Reionization appears to have been driven by an enormous population of smaller UV-bright galaxies, producing more ionizing photons than previously estimated. Webb's ability to detect and characterize these faint reionization-era galaxies is essential for understanding how the universe transitioned from dark to transparent, and the picture emerging is one of a faster, more efficient reionization than most pre-Webb models assumed. Another thread in the same direction. Another signal pointing toward an early universe that moved faster and organized itself more efficiently than our models predicted it should. 2 years of science from the James Webb Space Telescope have produced something more interesting than a catalogue of discoveries. They have produced a consistent signal running through dozens of independent observations across completely different targets, wavelengths, and measurement techniques. The signal is this: the early universe assembled itself faster, more organized, and more chemically complex than the best models built on established physics predicted. The galaxies were more massive, the black holes were larger, the structure was more ordered, the chemistry was more advanced, the star formation history was more intense and more rapid. The quenching happened earlier, the reionization was more efficient. Every one of these findings is still being studied. Every one carries uncertainties. Every one has competing theoretical explanations being actively evaluated. The standard model of cosmology has not been falsified. Dark matter and dark energy remain the best explanations for the universe's large-scale structure and accelerating expansion. The evidence for them is robust. What Webb is doing is finding the limit of what the current version of those models can explain. Every major telescope in history has done this. Hubble found evidence of dark energy. The cosmic microwave background experiments refined dark matter. Each generation of instruments revealed the edges of the previous framework. Webb is doing the same, at higher precision and at earlier cosmic times than any previous telescope could reach. The questions Webb has sharpened will take years to resolve. Some will be answered by Webb's own continued observations as more data accumulates and more spectroscopic confirmations arrive. Some will require the next generation of instruments, including the Nancy Grace Roman Space Telescope, which will survey enormous areas of sky with Webb-level sensitivity, and the extremely large telescope currently being built in Chile, which will combine a 39-meter mirror with spectroscopic capabilities designed to push into the earliest epochs of the universe. Some questions may require a genuinely new theoretical framework. That is the possibility that cosmologists are, characteristically, careful and precise about raising. They do not call it a paradigm shift unless the evidence demands it. The evidence Webb has produced so far demands revision and deeper investigation. Whether it demands something more fundamental will depend on what the next wave of observations reveals. What is certain is that the telescope is working. Every mirror segment is aligned. Every detector is performing. Every instrument is returning data that redefines what is measurable. Webb was built to see the first light of the universe, and it is seeing it, along with everything in between, with a clarity that keeps returning one consistent message. The universe got here faster than we thought, and the physics that explains how it did that is still, in important ways, being written.